This screencast is about identifying parent functions in different families of functions, and to be able to describe and use transformations of functions, translations up, down, left, right, as well as reflecting, stretching, and compressing those same functions. Let's look at the idea of parent functions. And we're going to look at four very common ones that are used in this part of algebra. The first one is something to the 0th power. That is a constant function, where f of x is some constant a. And the function of this looks like a horizontal line. This particular one is f of x equals 1. And so the domain of these functions is all real numbers. The range is only that particular number a. The linear function's parent function, often called the identity function, f of x equals x, is a line passing through the origin, and all points are coordinates a comma a. So this line has 0, 0, 1, 1, 2, 2, negative 3, negative 3. All those points on it. It has a slope of 1. It's the equation f of x equals x. That's the parent function of all linear functions. The absolute value function, which we learned about in a previous screencast, has this sort of V shape. It is a piecewise function in two parts, given by the equation f of x equals absolute value of x. Its domain is all real numbers. Its range, its output, is only positive numbers. And then we'll look at a second degree equation called a quadratic function, whose parent function is the graph f of x equals x squared. It is an upward-facing parabola. F of x equals x squared has a domain of all real numbers. Its output is also positive because when we square a number in the real number system, we always get a positive number or 0. Let's look at the different transformations that can be made to functions. And not just the four parent functions that we looked at, four families of functions that we looked at, but pretty much any function is going to behave like this. So this is a very universal concept. So the first group of transformations we're going to look at are called translations. You may remember that from geometry. So a translation is when we are shifting the graph of something, the image of something, left, right, or up or down. So the first two examples here are when we are changing the input of the function. So then instead of it being f of x, it becomes f of x plus or minus some number, let's call it h. We are then going to shift the graph left and right because we're changing the input of the graph. The second group of translations here, when a number is added or subtracted from the output part of the parent function, the f of x, so it's f of x plus or minus some number, then we're going to be shifting, translating the graph up or down. So we're going to look at examples of translations. Let's take a look at the parent function y equals x squared, the quadratic family of functions. If I needed to shift this graph to the right by 2, I'm going to have y equals the quantity x minus 2 squared. That will shift it to the right 2 because what's in that grouping, that parentheses, is what makes the 0 of the function. So if it's just x squared, then it's 0. But if it's x minus 2's quantity squared, then a value of 2 for x will make it 0. So it shifts it to the right 2. In a similar way, if I use the graph of x plus 2 quantity squared, I'm shifting it to the left 2. But because if I look at the grouping of x plus 2, substitute a negative 2 for x, that will give me my 0 and shifts the graph to the left. To translate a graph up and down, we're going to add the appropriate quantity to the end after the groupings. So if our parent function is x squared, f of x equals x squared, and I want to move that up, I want to translate that up by 3, I'm going to use f of x equals x squared plus 3. If I want to shift it down 3, I'm going to use x squared minus 3. Okay, so notice the difference. To go left or right, I'm changing the input inside the grouping. To go up or down, I'm changing the input outside the grouping. Let's look at a second type of transformation, and that's a reflection. To reflect a function about the x-axis or the horizontal axis, we put a negative sign in front of the function. And what that does is it takes any positive output, makes it negative. It takes any negative output and makes it positive. The result being that the graph gets reflected or flipped about the horizontal axis. So for example, if we take the parent function y equals x squared, that upward facing parabola, and we put a negative sign in front of it, what we have is every point that was on the original upward facing quadratic now has the same x value, but the f of x, the y value, has changed and become negative. So it creates this sort of evil twin across the horizontal axis. If we want to reflect a function about the vertical or y-axis, then we change the inside of the grouping and we turn it into a negative. So for example, if we have the parent function y equals x to the third power, or the cubic function, which looks something like this red curve here, and we want to reflect it about the y-axis or vertical axis, we put the negative x on the inside of the grouping. So negative x is now being cubed. When we do that and graph it, we see something that's reflected about the horizontal axis. The final type of transformation we'll look at is called a dilation. There are two forms of dilations. There are stretches and compressions. If we want to stretch a function so that it grows more rapidly, we're going to multiply it, the entire function, by a number greater than 1. So for example, if I take the parent function y equals the absolute value of x, and I multiply it by 2, the new function is y equals 2 times the absolute value of x. When I graph it, you see this green function that grows twice as fast. That's called a stretch, because essentially we're taking that function out and we are stretching it such that it grows faster. I can have the opposite effect of a compression by multiplying the entire function by a number between 0 and 1 so that it grows less rapidly. So for example, y equals 1/2 the absolute value of x. Looks like this blue function, and that's called a compression. I've multiplied it by a factor of 0 between 0 and 1. It's growing more slowly. So those are the two types of dilations: stretches for numbers greater than 1, and compressions for numbers between 0 and 1 that we're multiplying the parent by. Let's take all this and put it together. So I have a function like y equals negative quantity x plus 3 squared minus 2. And I want to analyze it and graph it, analyzing the transformations. Well, first of all, I have to identify the parent function. This is a second degree or quadratic function, so the parent function is y equals x squared. That's the parent. From the parent, we've done a lot of things. You can kind of go from left to right on this. We reflected it about the x-axis because the negative sign is in front of the grouping. So the negative sign will reflect it about the x-axis. We know that. So the second thing, looking inside the grouping here, is that we've got a plus 3. We've got an x plus 3. So I know that it has shifted it to the left by 3 because an x of negative 3 will make this 0. And then finally, I'm going to look over here on the right, and the negative 2 tells me that it shifted down by 2. So instead of having a vertex at 0, 0, it now has a vertex at negative 3, comma, negative 2, and then it's going to go down for there. So let's graph it and look at it, and indeed that's what happens. So we've looked at parent functions and how to transform them through translations, dilations, and reflections.